Hello, Emily. How are you?
Good, how are you?
I'm doing good too. Let's see. How is your Oakland class going so far?
Stressful.
Stressful? Yeah, I know. It's a lot of material. Like midterm is tomorrow on Thursday.
hmm
Yeah. Let's see. On the study guide, is there any like topic that you wanted to go over? Like anything that is
Um,
confusing you the most?
I would say so today I was doing a lot of the practice exam with like a tutor from well he's not really a tutor, but he does office hours here.
Mm-hmm. Yeah.
And from the practice exam I wasn't able to finish number seven
Mm-hmm.
or like the rest of it. So I was saying that besides I just want to, okay, so my first one I want to focus on is question number three quickly because we did
Mm-hmm.
do it. I don't know if you can
Yeah.
see my, oh, let me
Oh yeah,
see.
can you share your screen on Zoom, please,
Let
so I
me
could
see.
like see the
How
problem?
can I see myself? Oh, okay, there you
Uh-huh.
go.
Yeah.
So if you see, sorry if it's blurry, we did
Mm-hmm.
question number three from my
Mm-hmm.
practice exam, which was about arrow pushing mechanism, which I'm kind of bad at. Like we did it together, but
Mm-hmm.
I still wasn't really understanding him.
Yeah. Can you take a picture of that and
Put it in
send
the
it?
chat.
Yeah.
Okay.
Or like
Okay.
send it to like text message. Text message
Okay.
would be
Okay. So,
best. Yeah.
yeah.
Mm-hmm.
Let
Okay.
me see.
And then we'll go over that.
Okay. Wait.
Mm-hmm.
Because he was talking about like the hydride shift and stuff, which that's where I got lost on. Like I did not know.
Like what hydrogen shift meant? Mm-hmm.
hmm
Okay. Let me see. Okay, I got it. Let me airdrop it to my iPad. Okay. To everyone. Okay. Yeah. Okay. Let me share my screen again. Share screens. Okay. So number three, was a question that you had a problem with.
Yeah, I'm
Yeah.
just not really good at arrow. Like I just want
Uh-huh.
like full acknowledgement and like the
Uh-huh.
arrow pushing
With the
mechanism.
arrows, yeah.
Yeah.
So we have seen methods to convert halogens into alcohols. Um, this one, NaOH, yep, SN2, E2, um, HBr, no. Yeah. Okay. Yeah. Yeah. Unfortunately, the previous reaction suffers from a side reaction which produces the product shown. Yeah. Provide a complete arrow pushing mechanism. Hidden H hydro shift. Yeah. So let me show you this chart really quick, right? And this chart will help you with alcohol and strong acid reactions. So ROH is alcohol, and what depending on what type of alcohol you have, you're gonna do a different reaction, right? And there's gonna be three, like I mean, five different alcohols that you're gonna see. There's gonna be a methyl alcohol, and I'll describe what that means afterwards. But let me make a chart for you to put on your note card so that you could use that on the test tomorrow. You can have
hmm
a primary unhindered alcohol. You can have a primary hindered alcohol. You can have a secondary alcohol or you can have a tertiary alcohol, right?
hmm
And then I'll describe what they mean later, but if you have a methyl or primary unhindered alcohol, you're gonna get an SN2 reaction. If you um have um a primary hindered, a secondary or tertiary alcohol, then you're gonna get SN1 or E1 reaction. Okay?
Mhm.
Now, let me show you what each of these mean here. Okay? Okay. 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 So a methyl alcohol would be a CH3, that's the methyl group, OH, right? So let me just draw that out like this. Um, CH3OH. This is the methyl alcohol, right? Methyl meaning
Mhm.
CH3, OH meaning the alcohol.
Mhm.
A the difference between primary unhindered and the primary hindered is the hardest one to see, right? The primary unhindered alcohol is gonna look something like this, where you know how this OH here is the alcohol? That's the
Mhm.
alcohol right there. And this is the R group, whatever like the carbon is and the hydrogens, right? Um the alpha carbon is gonna be the first carbon attached to the alcohol. The beta carbon is gonna be the second carbon away from the alcohol.
Mhm.
Right? So look at the alpha carbon right here. You notice how there's only one other carbon attached to the alpha carbon?
Mhm.
Because there's only one other carbon attached to the alpha carbon, we call that a primary alcohol.
Mhm.
Right? Now the unhindered versus hindered is gonna come from the beta carbon. If you look at the beta carbon over here, ignore the bond to the alpha carbon and everything attached to that, right? You notice how the beta carbon here only has one group attached to it, one branch attached to it. Because that beta carbon only has one group attached to it, um, it's gonna be unhindered, not crowded, right?
Mhm.
Let me show you the primary hindered one, so then you see a difference between them. So if you have a primary hindered alcohol, this is what you would get. So we said earlier that this right here is the alcohol. The first carbon away from it is the alpha carbon. The second carbon away from it is the alpha carbon. The beta carbon, I mean. And then notice how the beta carbon here has two groups now attached to it. One, two. Like
Mhm.
one coming out here, another one coming out there. Because it's
Mhm.
branched, it's gonna be hindered now, meaning that it's crowded.
Mm,
It's
okay.
crowded, right? Hindered meaning crowded or
Mhm.
bulky. Okay. Uh, now, secondary alcohol would be if the alpha carbon is attached to two groups. So an example would be something like this. This right here is a secondary alcohol because if we look at the alpha carbon, which is the first carbon directly attached to the alcohol, has two groups attached to it, and those two groups can be random things. It doesn't have to be a methyl group like this.
Mhm.
It could be ethyl group like that, or it could be an isopropyl group or a tert-butyl group, any random group like that, right?
Mhm.
Now, a tertiary alcohol is going to be when the alpha carbon, which is the first carbon directly attached to the alcohol, is going to be attached to three other groups. So this is the alpha carbon right here, directly attached to the alcohol. It's attached to three other groups like that,
Got it.
right?
Okay, really quick, while we're on
Uh-huh.
that topic, I know this is kind of a little bit off track,
Uh-huh.
but if you see on my screen over, oh, I think I can see me now.
hmm
Okay.
Yeah.
Sorry, I can't see myself. Give me
hmm
1 second. Okay. Um, are you able to see this?
Yeah,
So
I'm able
this
to
was
see
just a
that.
practice quiz,
hmm
and it's just saying like for the following reaction,
hmm
just like make the mechanisms of SN1, SN2, E1, or E2.
hmm
For this, when I'm
hmm
naming the like if it's primary, secondary,
hmm
this would be secondary or because there's two carbons, like I put little dots on them.
hmm Yeah, that would be secondary.
Would this one also be secondary as
That would
well?
also be secondary as
And then this
well.
one's tertiary.
Correct.
Okay. And then
hmm
really quick. Oh, actually, I'll let you go back to that and then we can go back to this after.
Okay, yeah, and we could
Okay.
go do the SN1, E1, E2
Yeah.
reactions as
Mhm.
well.
Yeah.
But I want you to definitely put this on your note card.
Okay, okay, okay.
Right here, like this chart that I'm about to add on your notes, which I will send to you afterwards, like will tell you exactly what reaction you need to do. Like it's if it's gonna be a SN2 reaction, A2 reaction, SN1 E1 reaction, they always go together. When SN1 reaction, E1 will always go together. Depending on what reagent you have, right? Which is like either a weak base strong nucleophile, small strong base strong nucleophile, bulky strong base strong nucleophile, weak base weak nucleophile, or a good leaving like a good leaving group, right? And what
Mm-hmm.
type of substrate you have, like a methyl one, primary unhindered one that we just talked about, primary hindered one, secondary substrate, tertiary substrate, and then depending on that, it will tell you what reaction you have. And then here's some examples and like the mechanism of each reaction. SN1 E1 over here, E2 reaction over here, and then SN2 reaction over here. And it just describes how it works with
Mm-hmm.
examples on each. Okay.
Mm-hmm.
Okay. So now if we go back over here, let's talk about carbocation. Are you familiar with the term carbocation, Emily?
Now I am a little bit, but
Mm-hmm.
I know that that's like the main reason for SN1 is just like the focus is carbocation.
Mm-hmm. Yeah, the main focus for SN1 and E1
Mm-hmm.
is gonna be carbocation because in the mechanism, meaning that like what happens in the reaction behind the scenes is that a carbocation intermediate is gonna form. So it's something called a carbocation is going to be formed in the mechanism behind the
Mm-hmm.
scenes, right? So carbo meaning carbon, cation meaning positive charge. So cation is positive charge. So if you see a carbon with a positive charge, that's a carbocation,
Mm-hmm.
right? And then there's gonna be different types of carbocations. There's gonna be methyl carbocation, primary carbocation, secondary carbocation, and tertiary carbocation.
Mm-hmm.
Right. So a methyl carbocation would be something like this, a CH3 with the positive charge on the carbon right there. A primary carbocation would be if this carbon here that has the positive charge is attached to one other carbon. Right? It's just
Mm-hmm.
like how you determine primary, secondary, tertiary for
Mm-hmm.
like haloalkanes, for alcohols. It's the same exact thing. Like how many other carbons it's attached to. This is a secondary carbocation because it's attached to two other carbons like that. Right. Now, this right here is a tertiary carbocation, and then I could draw it out like this because it's gonna be more typical to be drawn like this. This
Mm-hmm.
carbon here has a positive charge because it's attached to three other carbons, one, two, three, like that.
Mm-hmm.
Okay. Now, think about which one is more stable. The more substituted the carbocation is, the more stable it's gonna be. Right. So this is the most stable carbocation because it's the most substituted. There's more groups around it. This is the least substituted carbocation, so it's the least stable carbocation. Right.
Mm-hmm.
And
Mm-hmm.
then if he asks like because why, like just say hyperconjugation, right?
Mm-hmm. I remember
Hyperconjugation,
we went over that. Mm-hmm.
right? Okay. Now let's go over the mechanism of SN1 really quick. Right? So for SN1 we need a good leaving group and then we need a weak nucleophile, which is all in that chart right there, which I recommend putting that chart in your note card, right? So
Mm-hmm.
is this a is methyl primary, secondary, or tertiary substrate?
That is going to be a secondary.
Uh-huh. Secondary substrate. We have a good leaving group present, which is the bromine. We have water here, which is a weak base, weak nucleophile, which all of those information will come together and give us SN1 E1 reaction, right? And for SN1 E1 reaction, the very first step of the mechanism is to kick out the leaving group. Okay, so I'm just gonna add this group here, just to show you like this very important step right here. When we kick off the leaving group, you see this bond here between the leaving group and substrate, the secondary carbon right there.
Mm-hmm.
That bond is gonna go onto the bromine. Like the two electrons in that bond are gonna go away with that bromine. So they're just gonna float away, right?
Oh, okay.
That's the very first step of the mechanism. Like the leaving group leaves with the bond it's attached to, the substrate. Okay.
Okay.
And you know how this carbon here lost the bond, which is this one here, it lost the bond
Mm-hmm.
when the leaving group left. Because it lost the bond, it lost electrons, right?
Mm-hmm.
Because the bond has two electrons, so it's gonna lose those two electrons. And because it's losing negative charge, that carbon is gonna be a positive charge,
Got it. Okay,
right?
now that makes sense.
hmm
Mm-hmm.
And this is
Okay.
what we call a
Cat.
carbocation. Right. And what kind of carbocation do we have here? Um, Methyl, primary, secondary, or tertiary?
We have a primary.
So if we look at this
Wait.
carbon here directly, how
Oh,
many other
sorry,
carbons?
secondary. Secondary.
Secondary.
Sorry,
Uh-huh.
sorry.
Secondary. Correct. Correct.
Mm-hmm.
Uh-huh. So if you look at where it is in stability wise, it's like right here in stability, right?
Mm-hmm.
Whenever you form a carbocation intermediate, right? Like don't do anything else. You have to stop. This is the common mistake most students make, right? You gotta stop and look out for something called a carbocation intermediate. Oh no, carbocation rearrangement.
Okay. Enter. Oh,
Rearrange.
wait.
Yeah,
Rearrangement.
rearrangement. Right. And rearrangement meaning that we're gonna arrange the carbocation somewhere else. Right. So look directly to the left of it. If we moved the carbocation to this position, would it become more or less stable?
I'm so sorry. Can you say that again? It cut out.
Yeah. So you know how our carbocation we have right now
Mm-hmm.
is this one?
Mm-hmm.
Look directly to the left and right of it. Let's focus on the left of it, which is this carbon
Mm-hmm.
right here.
Mm-hmm.
If we move the carbocation right there, would it become more or less stable?
Wouldn't it become less stable?
Mm-hmm.
Since then it
Yeah.
would become a primary,
Yeah.
and that
And
would
we
make
don't,
it less stable because
yeah.
tertiary is
Mm-hmm.
okay.
Wait, how about to the right?
To the right, it would make it more stronger because it would become,
Uh-huh.
or actually, hold up, give me one second. One, two. Wouldn't it still stay the same?
So there's one, two, three.
Oh, okay. Okay. Hold
Mm-hmm.
on. Let me see how to do that.
Mm-hmm.
Okay, so we're starting. Oh, okay, I thought you meant that as the end. Okay, yeah, it would be
Mm-hmm.
tertiary, which need yes, it would be the most the
Uh-huh.
strongest.
Yeah, most stable. So we want the carbocation in that position.
Okay.
Right. So we want to rearrange that carbocation in that position. But we cannot do this. Do not draw the arrow from the positive charge to that carbon right there to show that moving there. Right?
Mm-hmm.
Because do you know what the arrow represents? Like what in the mechanism?
Mm-mm.
So arrow, right? Whenever you see an arrow like this in organic chemistry, that arrow is going to show the movement of two electrons. That's what the arrow means.
Arrows.
Hmm.
Okay.
Movement of two electrons. So you know how this is a single bond right here?
Mm-hmm.
There's two electrons in that single bond.
Got it. Okay.
The two electrons in a single bond are going to the bromine,
Mm-hmm.
like that, right?
Mm-hmm.
So that's why the bond is no longer there because it went away to the bromine, which the bromine is a side product with a negative charge. It's just floating around somewhere nearby.
Mm-hmm.
Okay. Okay. So now because there's no electrons there, we cannot draw that because there's a hole here, like an empty void right there. Okay.
Mm-hmm. There's nothing that we can move. Yeah.
Right. Now this carbon here, how many bonds do you see right now? That with your eye?
Three.
Three, right? One, two, three. Do you
Mm-hmm.
know how many bonds it wants to become neutral?
Mm. It would be two bonds, right?
To become neutral, carbon wants to have four bonds. Every
Oh,
carbon
four
wants to have
bonds. So
four
two.
bonds to be
Can
neutral.
you explain that a little bit more,
Uh-huh.
really quick?
Yeah. Yeah. So to that's gonna go into four more charge, right?
Oh, again. Okay.
Yeah, yeah,
Okay.
four more charge. And you have to look at the periodic table. Do you remember what carbon is gonna be at like what group on the periodic table?
Wasn't it six? Or...
Oh, six will be oxygen.
Okay. Oh,
Will be
yeah, yeah.
oxygen.
Wasn't it four?
Yeah, four. So that means that carbon wants to have four electrons to itself, right? So let's say we have this carbon right here,
Mm-hmm.
and carbon here is going to be neutral because it has four electrons to itself. One, two, three, four, right? So four, how much it wants minus how much it has, four, zero, neutral,
Mm-hmm.
right?
Mm-hmm.
Um, we see that this carbon here is also neutral because we don't see any charges to it. We don't see a
Mm-hmm.
positive charge. We don't see a negative charge. And
Mm-hmm.
because it's neutral, how many bonds does it have?
Mm,
Don't look up, don't think about what you see. Think about like how much it should have if it's neutral.
four.
Four bonds right now, but we only see three.
Mm-hmm.
So there's one missing one,
Mm-hmm.
right? And that one missing one is the invisible hydrogen.
See, that's what he was like talking about too, was an
Uh-huh.
invisible hydrogen.
Right, because this right here is bond line structure. Like whenever you see diagrams like this on OChem,
Mm-hmm.
like right, like
Mm-hmm.
that, or like this, or like
Yeah, it's
that.
just like the skeletal structures never show the hydrogen anymore.
Yeah, like the hydrogens are always invisible unless like it's coming from a functional group, like an aldehyde, like that,
Okay.
or a carboxylic acid, like this.
Mm-hmm.
Right. Now let's do some practice here. Now each point here, right, represents a carbon atom.
Mm-hmm.
Carbon, 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 carbon.
Mm-hmm.
And you know how all of these carbon atoms are neutral? There's no positive charge, there's no negative charge.
Mm-hmm.
Because of that, how many bonds would the carbon should the carbon have?
Four.
Four. Right. Let's look at this carbon specifically. How many bonds do you see for this carbon?
Um, two,
Two. So how many is it missing right now that we don't see?
two,
Two.
two.
Those two bonds are bonded to hydrogen. They're hiding from you.
Mm-hmm.
Yeah, they're invisible. Let's try this one here. How many hydrogens are in this carbon here?
Um, mm, there, hold up.
Mm-hmm.
There should be three, right? Three.
There's three hydrogens hiding from you for this carbon
Mm-hmm.
because
Mm-hmm.
we want that carbon to be neutral, but we only see one bond, right?
Mm-hmm.
So, but we know it should have four because it's neutral,
Yeah.
but we only see one, so three are hiding from you. So those three hiding
Mm-hmm.
from you are the hydrogen bonds, like that.
Mm-hmm.
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 Right. Now let's do a little bit trickier one. Let's try this one right here.
Mm-hmm. One, two. There's one missing.
Mm-hmm. So that means there's one bond to hydrogen like that,
Mm-hmm.
right? This double bond here counts as two bonds.
Mm-hmm.
Okay. Now how about this carbon? How many hydrogens should this carbon have right here?
Um, none.
None. Yeah, there's zero bonds to hydrogen because it already has
Mm-hmm.
this four bonds. It already has this octet rule filled.
Mm-hmm.
Right.
Mm-hmm.
Now, how about this carbon right here?
None as
None
well.
as well. Yep, yep. So this triple bond carbon here, one, two, three, has four bonds already. One, two, three, four. So no
Mm-hmm.
hydrogens right there.
Mm-hmm.
Nice. Okay. Now, if we go back over here, how many hydrogens does this carbon have?
Mm, which one? Oh, there.
Mm-hmm.
It technically has four, but there's one missing.
Mm-hmm.
So just one more hydrogen.
Yep, one hydrogen, which I'm gonna draw out explicitly like that and not make it invisible, but it's always there, right?
Yeah, yeah, yeah.
But most people just draw it invisible, but I'm gonna draw it out in the mechanism because
Hmm.
you know how we said earlier that we want to move this. Let me just label it. It's secondary carbocation to this position. That's tertiary,
Hmm.
right? Um, so to do that, I'm going to move this hydrogen with the bond
Hmm.
to that carbon right there.
Okay.
Right, because you know how this arrow here represents the movement of two electrons?
Hmm.
The
Hmm.
two electrons on this bond here are gonna move onto that position right there.
Hmm.
Right? Because right now, how many hydrogens does this carbon have? This is a little bit tricky. This
Hmm.
positively charged carbon here have. It's not neutral. It's not neutral.
It's not neutral, so
Yeah.
that means that
Four minus
four minus
what is
five.
plus one?
Oh
Four
wait,
minus
plus
five is
one?
negative one. Yeah.
Okay. So well, it would be so if we're doing negative, we'll have to get it to positive.
Mm-hmm.
Wouldn't we add?
Yeah. Let's think about how many before we do this hydrogen shift stuff. You know how this carbon here is positively charged, right?
Hmm.
Um, a neutral carbon, we said it wants four electrons to itself because it's on the fourth group, right?
Yeah.
And then four minus, let's say X, we don't know how many bonds it has, is equal to positive one because we see it has a positive charge right there, right? So do you
But
know how we can solve for X here?
what's confusing me is
Mm-hmm.
that wouldn't you add? Oh wait, sorry, no, you're right.
Mm-hmm.
You at the minus five, right? No, but that means it would be negative one. We want positive.
Mm-hmm. Yeah, it wouldn't be positive. So four minus what number would be positive one? Because four minus five is negative one. We don't want negative one.
No, 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 you're right.
Yeah.
For what? Oh, I know it's super easy, but I'm just like
Uh-huh.
confused right now.
Yeah, yeah. It's okay. Four
Four,
minus um three.
three. That's what I'm gonna say.
Mm-hmm.
Three.
Four minus three.
Oh my gosh, I don't know why I keep thinking like negatives. Okay, no, no, no.
Uh-huh.
Yeah, four minus three obviously is like
Uh-huh.
one.
Yeah, four minus three is
I
one,
keep
correct?
thinking the four is the negative. Okay,
Oh,
yeah.
yeah, four is negative. Yeah, yeah, four is not negative.
No,
Right?
yeah, yeah.
Yeah. Uh-huh. So that means that this positive charge carbon here should have three bonds, not four
Mm-hmm.
bonds, right?
Yeah,
How many bonds do you see right now?
two, but we're
Two.
missing one more.
Yeah, so this carbon here has only one hydrogen bond,
Mm-hmm.
right? One hydrogen bond, which I'm going to draw out like that.
Mm-hmm.
Okay? Now, it would like to gain another bond to become neutral and stable.
Mm-hmm.
Right? Because with the positive charge, it's very sad and angry. Right?
Yeah.
It doesn't like atoms don't like charges at all. They want to become neutral and stable.
Mm-hmm.
Right? So you know how nearby we said like that's where the positive charge could be more happy at?
Mm-hmm.
To do that, this hydrogen right here with the bond, like this bond right here, you see this bond right here that I'm highlighting?
Mm-hmm.
Yeah. The two electrons and that hydrogen right there are gonna go to that carbon right there. So we're gonna give this carbon an extra bond with that hydrogen right there,
Mhm.
right? Does that make sense so far? Like what this arrow represents? Like we're
Mhm.
moving this entire highlighted part, like the bond and the hydrogen, to that carbon right there. We're giving
Mhm.
this carbon a bond and a hydrogen,
Mhm.
right? So this is what we would call a hydride shift
Mhm.
because we're shifting the hydride over.
Mhm.
Okay. And then as a result, after that hydride shift, this carbon here to the left, I'm gonna highlight the bond with the hydrogen that we moved, which is this one right here. Now
Mhm.
has how many bonds do you see?
Four, so it's neutral.
So it's
It's
neutral.
happy.
It's happy now. But how about this carbon? It just lost the bond. They,
So it's not happy because there's only three.
only three. And what should the charge be now?
The charge should be positive right there.
Positive charge. Yeah. And what kind of thing intermediate is this called right here? When you see a carbon with a positive charge?
The carbon cation.
Yeah, carbocation. And what type of carbocation is this?
The tertiary one,
Tertiary,
which means
right?
it's stable.
More stable, right? More stable than it was before. Before we had a secondary carbocation,
Mm-hmm.
now we have a tertiary carbocation. That's why we did the hydride shift. So we could get a more stable carbocation like that,
Okay,
right?
perfect.
Okay. So now from there, after we got that hydride shift, right? We could bring in the nucleophile, which is the reagent on the arrow, water,
Mm-hmm. Mm-hmm.
right? H2O. And we know oxygen here will have two pairs of electrons
Mm-hmm.
because it's neutral like that, right? You know how we
Mm-hmm.
said an arrow represents the movement of two electrons?
Mm-hmm.
We're gonna move a pair of electrons, so two electrons on the oxygen here, to attack this carbon right here,
Got it. Okay.
right? Because this carbon here really wants to gain a bond to become neutral,
Mm-hmm.
right? So this is what we call an electrophile. We know how we said electrophiles are positive charge. That
Mm-hmm.
carbocation is an electrophile. This right here is a nucleophile because it has electrons that it could use to attack an electrophile,
Mm-hmm.
right? Okay, does that make sense so far?
Mm-hmm.
Okay. Now, as a result, I'm gonna highlight this pair of electrons to make it more clear. This is gonna be, let's say, red, right? And now I'm gonna make the hydrogens invisible. I'm not gonna draw those hydrogens anymore because it's gonna make it crowded. Okay.
Mm-hmm.
So, like that, like that, like that. Now, this bond here that I just drew out is the new bond. That bond wasn't there before. But you know how I highlighted it red?
Mm-hmm.
The two electrons in this bond here came from the two electrons on this oxygen right there.
Oh, how do we know when to like where to put it? Is that just because it just makes sense like
Oh
that?
yeah, you could put it here, 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 or here. It doesn't matter.
Okay.
Yeah, you could put it anywhere, right?
Okay.
You could have put it right here if you wanted to. It would have been the same thing.
Okay. Got it. Got
Okay. Yep. Now you know how the oxygen here used the pair of electrons to attack that carbon right there with its pair of electrons? This carbon here is now attached to that oxygen. This oxygen here that is drew out is this oxygen right here,
it. Mm-hmm.
right? Now, what else is attached to this oxygen right here?
Um,
Uh-huh.
another pair of electrons.
Uh-huh. Another pair of electrons and two hydrogens,
Mm-hmm.
right? So I'm gonna draw the two hydrogens out like this. One, two.
Mm-hmm.
Right. So if I highlight the water in blue like that with a pair of electrons, that's gonna be this blue water with a pair of electrons like that.
Mm-hmm. Mm-hmm.
Right. Now, you said earlier that oxygen is on the sixth group of the periodic table, so it wants
Mm-hmm.
six electrons to itself. What form of charge should this oxygen have? How many electrons does this oxygen have right here?
It has. Okay, my thing with that is
Mm-hmm.
it's only the ones that it owns, right?
That it owns,
Okay,
right?
so it has one, two, three, four. It's missing two more, right? Or
One, two,
oh,
three,
sorry. I
four,
keep forgetting that
five.
part. Yeah, I keep
Uh-huh.
forgetting the one on the red. Okay.
Yeah, this one right here.
Okay, that's
Yeah,
why I
yeah.
keep forgetting.
Uh-huh.
Okay, so it has five and it needs six, so it needs one
Mm-hmm.
more.
Mm-hmm. It needs one more, but if we do six minus five, that is
That is positive one still.
what? So it's positive charge. So this oxygen here would be positively charged,
Mm-hmm.
like that. So
Mm-hmm.
when you see an oxygen with three bonds like this and a pair of
Mm-hmm.
electrons, that oxygen will always be positively charged.
Got it. Okay.
Yeah. Is it stable or unstable? The oxygen with the positive charge.
I would say it's unstable.
Unstable, right? Because oxygen doesn't want that charge at
Yeah,
all.
it wants to be neutral.
It wants to
Mm-hmm.
be neutral, right? So we can neutralize this. We can make this positive charge neutral,
Mm-hmm.
right? So to do that, we have to deprotonate it. So a proton, right? Let me just define what this means. Proton, think of that as a hydrogen, H.
Mm-hmm.
This oxygen here has two protons.
Mm-hmm.
One, two. So we want to deprotonate it, right? Deprotonate it, meaning we're going to take away a proton,
Mm-hmm. Mm-hmm.
right? So this proton here is an acid, right? It's an acid. So to take it away, we need a base. And there's two bases that you could use. You could use another water molecule, right? Because we have a lot of this around in the solution since it's on the arrow,
Mm-hmm.
right? Or you could use you know how in the very first step we kicked out the good leaving group right there?
Mm-hmm. The bombing. Mhm.
The bromine. The bromine minus here could be the base. Like you could use one of these, H2O or Br minus,
Okay.
right? Um, I'm gonna use H2O here because that's the more accurate one because there's a lot more of that than Br minus, right? That H2O here is going to grab one of the protons like that, right? What does this arrow mean again?
Like it's getting the
Hmm.
electrons
The electrons are moving
moving
towards the hydrogen. So the
towards.
electrons on this oxygen here are moving towards that hydrogen to grab it,
Mm-hmm.
to
Mm-hmm.
make a bond with the hydrogen right there. But
Mm-hmm.
to grab it, you know how this hydrogen is already bonded to this oxygen?
Mm-hmm.
Those two electrons on that bond right there are gonna break away and go onto the oxygen like that.
Wait, can you explain that again? Sorry.
Yeah. So, how many electrons are in this bond right here?
Two.
Two electrons, right? Um, what is this arrow representing?
It's donating the
Uh-huh.
electrons to the hydrogen.
Yep, it's trying to make a bond with the hydrogen, right? This
Mm-hmm.
oxygen here is trying to grab the hydrogen,
Mm-hmm.
but hydrogen can only have one bond,
Mm-hmm.
right? So like this oxygen here is trying to grab this hydrogen, but this hydrogen is already grabbed by this oxygen right here,
Mm-hmm.
right? So when this oxygen is grabbing this hydrogen here, this bond is gonna break,
Mm-hmm.
right? So in order for this oxygen to have that hydrogen bond right there,
Yeah.
right? But it cannot just like disappear in thin air. It has to go somewhere, right? Because how many electrons are in this bond right here?
Two.
Two. Where do you think those two electrons are gonna go to if this hydrogen is being grabbed away by this water right here?
Wouldn't it grab onto the oxygen?
Yeah, the two electrons right here on this
Yeah.
bond are gonna go onto the oxygen like that,
Yeah.
giving that oxygen another pair of electrons.
That's a lot.
Uh-huh. Right? Yeah,
Mm-hmm.
so I'm gonna draw out the result, which would look like this. Okay? Does this make sense so far on how I got to here?
Mm-hmm.
Right? So you know how before this oxygen here had two protons, two hydrogens,
Mm-hmm.
but now it only has one proton, and
Mm-hmm.
we know how before it used to have only one pair of electrons,
Mm-hmm.
but now it has two pairs of electrons, and I'm highlighting it pink, right? Because that's the new one right there, which came from this bond right here,
Mm-hmm.
right? Now, if you look over here, you know how this oxygen here, this water here became that H3O plus right there, right? This oxygen here will be positively charged because it has one, two, three, four, five
Mm-hmm.
electrons itself. Six minus five is positive one,
Mm-hmm.
right? And this is a byproduct, a side product. We don't have to worry about that. Okay. Um, Now that's our SN1 product right there.
Got it.
Does,
Okay.
does that make sense?
Yeah.
Okay. Yep. So can you describe to me a step by step what happened from this SN1 reaction? Let me zoom
Um,
out. Mhm.
like explain each step now.
Yeah. What's the very first step?
The very first step is going to be kicking, well, knowing like the leaving group, of
hmm
course.
hmm
And then from knowing the leaving group, we're gonna go ahead and then, um, hold up, good leaving
hmm
group. No, or actually, yeah, knowing the good leaving group, and then actually like naming it if it's like primary, secondary, or
hmm
tertiary. In this case, it was a secondary, so we knew it was gonna be either SN1 or E1, right?
Secondary reaction, it could also work on SN2 and E2 reaction,
Ooh.
but we know it's an SN1 E1 reaction specifically because we're using water.
Okay, and because water is neutral.
Yeah, and then if you look back at this right here, which I recommend you looking at for the test, right? Water is WbWn, which is a weak base weak nucleophile,
Got it.
right?
Okay. Okay.
WbWn, and it's a secondary substrate, so that tells us that it's a SN1E1,
Got
right?
it. Okay.
If you had any other reagent, it could be E2 or SN2.
Got it. Okay.
Yep.
And then from there, we're gonna go ahead and draw the arrow, and then we're gonna
hmm
start with the carbocation.
hmm
Um, so we place it where the bromine was at,
Mm-hmm.
and then from there we have to stop because we're gonna have to look for carbocation rearrangement,
Mm-hmm.
meaning that since it's a secondary, it's not as stable, and we want it to be more stable. So then we
Mm-hmm.
look to see where it would be, which of course it would be down there.
Mm-hmm.
Um, but we can't do that right
Mm-hmm.
away. So then we have to look for our
Mm-hmm.
hidden hidden hydrogens,
Mm-hmm.
because that's just three bonds, and it has a fourth one, of course. So then after that, we want to go ahead and then move that. So that's called a hydride shift.
Mm-hmm.
Um, so we get our arrow and kind of see that part. I don't know how to explain that. Like, how are you moving the arrow up
Mm-hmm.
there? Is it just? I know it's
Oh,
a hydride
for
shift.
this one
Yeah.
right here. Yeah.
Yeah.
So, if you look the difference between this molecule and this molecule here,
Hmm.
right? Let's
You're
let's
just
let
moving.
yeah, let's call this carbon A and it's carbon B.
Hmm.
Carbon A and carbon B. Carbon B has this bond with the hydrogen that I highlighted right there. We're
Hmm.
just moving the entire bond with the hydrogen to
Hmm.
this carbon A right here. That is missing a carbon to become
Hmm.
neutral. So now we see carbon A here has that hydrogen with the bond that I highlighted. So now because it has four bonds, it's neutral now. But before this carbon B had four bonds, right? One, two, three, four. And that's why it was
Hmm.
neutral and happy. But because we shifted this whole hydrogen bond to this other position here, this carbon B now has three bonds and is positively charged.
Okay.
Right. But this positive charge on carbon B here is tertiary, right? Which is more
Hmm.
stable than a secondary
Yeah, of course.
carbocation.
Hmm.
Yeah. So that's why we did that hydride shift.
Hmm.
Mhm.
Okay.
Yeah. Okay.
And then we do the hydride shift, third carbon. The thing is,
hmm So
now
a
we
way
have
that I
to.
recommend studying for this exam also is like whenever you do practice problems, right? Like from the practice midterm, to make sure you understand it, try explaining it to yourself again, like what happened in each step, so that you understand it. And if you get stuck, that's where you know where to study, what to study.
Hmm.
hmm Yeah. So from here, once you have the most stable carbocation intermediate, what do we do for SN1, SN1 product?
For the SN1 product,
hmm
well, don't we have to, or is this part where we add the H2O to it or no?
Yeah, this is where we bring in the nucleophile, whatever the nucleophile is on the arrow,
Which is
right?
H2O.
Which is H2O. It doesn't have to be H2O. It could be ROH like that, but in this case, it's H2O, right? Okay.
Mm-hmm. So then that, that it has, um, we have to use the arrows because we're moving the electrons
Mm-hmm.
from the O, but there's two pairs, so we move one pair first, and then we use the arrow pushing mechanism for that the carbocation,
Mm-hmm.
which then you draw it again, and that shows that going on. Mm, sorry,
Mm-hmm.
there's just kind of like it's all like
It's
switching
everywhere.
to
It's all over
yeah,
the place, right?
yeah.
Yeah.
Um,
Um,
the
so this oxygen here has two pairs of electrons, right? One, two.
mhm,
And because that's electrons, that's what we call the nucleophile,
mhm,
right? The thing that's negatively charged. And this carbocation here is the electrophile because it's positively charged, right?
mhm,
And in OChem, nucleophile always attacks electrophile, right?
mhm,
Because electrons are the ones that are moving. They're very like hyper. Electrons are very hyper. The negative
mhm,
charge things are very hyper,
mhm,
right? So the negative charge here, or like the electrons here on this oxygen, sees this positive charge that is missing electrons, and it really wants electrons right now to be
mhm,
neutral.
mhm.
So
Yeah.
that's why this oxygen here is going to like make a bond. Like the electrons here are gonna gravitate towards that positive charge right there, that void right there, right?
Mhm,
And that's what we call like attack, right? The electrons are gonna attack that carbocation to make a bond there,
mhm.
right? And that bond right there is this red bond right here, which came from this pair of electrons right there, like that.
Mm-hmm.
right? Okay. Does that make sense? Like how we got to here?
Yeah.
Okay.
Okay.
Hmm.
And then we show that. So then we have to draw like a whole new bond because
Hmm.
showing the because okay, since we move those two
Hmm.
electrons from there, we still have our two hydrogens and then we have our oxygen with just two pairs now. So we have to show that in like a new
One pair of electrons, which is two
oh
lone
yeah, sorry, one
electrons.
pair of
Hmm.
electrons, but two, yeah.
Yeah. Hmm.
So we have to show that
Hmm.
in a new bond right there. Mm, and then from there, hold up.
Hmm.
One, two, three. Okay, now I'm confused again.
Hmm. So once we have this right here, um, we calculate the formal charge of oxygen, right? Because oxygen is on the sixth group, it wants six electrons to itself. How many electrons does this oxygen have right here?
One, two, three, four, five.
Hmm.
Yeah, five.
Yeah. So six minus
And
five is
one, but it doesn't want to
hmm
be one. It wants to be neutral.
it wants to be
Mm,
neutral. So to neutralize it, we gotta deprotonate it. Deprotonate it,
mm-hmm,
right? And to deprotonate it, we need a base. And
mm-hmm.
the base can be one of two things. It could be water or
Okay.
the Br minus that we kicked out earlier, the good leaving good that we kicked out earlier.
Basic. Each water was more accurate.
Hmm. Because there's more of them and
Yeah.
yeah.
And so it kind of wants to attach to that hydrogen.
Hmm.
And then
And
from
then
there,
when this hydrogen is being grabbed, what happens to this bond right here between the hydrogen being grabbed and oxygen? Where does it go?
it disappears
Uh-huh. Where does it disappear into? Like it
into.
can't disappear into thin air. It has to go somewhere, right? The
Mm-hmm.
two electrons are gonna
Doesn't that
go.
pop onto the
Yeah,
OH?
it's gonna pop onto the OH
Yeah.
like that, and that's where the OH there gains a pair of electrons. And if you calculate the formal charge now for this O, what should the formal charge be?
Mm,
Right, like it does have to be drawn like that. It can be drawn like this, but we know that there's a single bond between the O and H right there.
mm-hmm. Isn't that one two though?
So
Mm,
because it's a single bond there, that's one, two, three,
yeah.
four, five,
Five, six.
six.
Uh-huh.
Yeah, six minus six,
Zero.
0. So this oxygen here is
Neutral.
neutral. Yep.
And king.
Hmm. Okay. So that's SN1. But the important thing here for SN1E1, you know how we said that it will always form a carbocation intermediate,
Mm-hmm.
right? And you know how we talked about carbocation stability here.
Mm-hmm.
Uh, the methyl carbocation and primary carbocation, they're in the lower half of the
Mm-hmm.
stability. They're like the least stable, right? And because of that, they are too unstable to form or exist in nature.
Mm-hmm.
Okay. The things that can form or exist in nature by itself are going to be secondary or tertiary carbocation. Okay.
Mm-hmm.
And that will come in handy when we talk about this next thing, which can be a little bit tricky, right? Let's say we have something like this. Using the chart, analyze this reaction and determine if it's going to be SN2 reaction, SN1E1 reaction, or E2 reaction,
Um,
or no reaction.
Let me see the chart. Give me 1 second. Are
Mhm.
you able to pull up that chart? Because I don't have it on my end now.
Yeah. Let me do it here.
Okay, let me screenshot that.
Mhm.
Okay. Oh wait, hold up. Sorry, it moved.
Yeah. Uh-huh. Mhm.
Okay, perfect. Okay, that is one. That's primary.
Mhm. Oh, there's two types of primaries. This is going to be very important for
Oh
this
yeah,
next
yeah.
topic.
Yeah. Let me
Mhm.
see which
Yeah.
primary it is. I would say this is primary unhindered.
Uh-huh. Primary unhindered.
Unhindered, which
Hmm.
makes it. Let me see the. I would say that has a. Wouldn't that be a weak base? Or.
Hmm. So this right here is an alcohol R, because the R can be any random hydrocarbon chain,
Mm-hmm.
right? OH, ROH is right here. Weak base, weak nucleophile, right?
Mm-hmm.
Because there's also weak base, strong nucleophile, but this specifically is a weak base, weak nucleophile because it's ROH.
Mm, okay. So then we know that is no reaction.
No reaction. And let me tell you
Mm-hmm.
why, right? So you understand it, instead of like looking at this right and memorizing it, right?
Mm-hmm.
Um, if you try to do SN1, right? What was the very first step of SN1 reaction?
To like look for the primary, secondary, or the leaving group part. Which
Yeah,
one?
that's the first part of analyzing it to determine that it's SN1E1, right? But then once we know that it's SN1E1, what happens to the leaving group?
You gotta kick it out.
We kick it out with the bond that it's attached to, right? So this is the bond that's gonna leave with the leaving group because the leaving group won't just leave by itself. It's gonna leave with the bond that it's attached to, right?
Mm-hmm.
How many electrons are in that bond?
Two.
Yeah. So if we kick it out, and let's say what would be formed as a result, like what charge should this carbon have here if it's losing that leaving group?
Do I have to go on the periodic table to know which group it's in?
So we know this is carbon right here, right? And this carbon here is neutral right now because we don't see any charges, right?
Yeah.
If it loses a bond, it's gonna be positively charged,
Oh, okay. Yeah.
right? So if I draw that out right there, like if I color code that pink carbon right there, which is the substrate carbon,
Mm-hmm.
the primary unhindered carbon, and there's a positive charge right here. What is this intermediate called right here?
Intermediate
Like, what do we call a carbon with a positive charge?
carbocation.
Uh-huh. Yep, carbocation. What kind of carbocation is this?
It's as a primary.
Uh-huh. And what did we say about primary carbocations? Are
They're not
they,
strong at all.
yeah, they're not stable at all.
Mm-mm.
We cannot form that at all.
Yeah.
Like this is not
Formable.
able to
Yeah.
exist. That's why it's
Got
no
it.
reaction.
Got it. Okay.
Right? That's why it's no reaction. Okay.
Okay. Okay.
But now let me show you a trickier example, which I'm going to use the example of the practice exam that you showed me,
Mm-hmm.
we're going to do a mechanism for that as well.
For which question?
Oh, actually, that was question number three, like the one that you showed me on the practice exam. Before we go
Mm-hmm.
over that, I wanted to give you a simple example. So then, I'll have you like look at the simple example as reference, and then go to the practice exam, and then do that based on this example that I'm gonna give you here.
Mm-hmm.
Okay. So then, when you see it on the test, you see a different R group, a different hydrocarbon chain. Yeah, you won't get lost.
Okay.
Right? Okay. So let's say we have something like this, and then H2O. Looking at the chart that I recommend you to put on your note card, what kind of reaction would happen here?
Let me see. That is going to be a primary. So it'll be a primary, but wouldn't it be a hindered one though?
Uh-huh. Primary hindered, correct?
Primary hindered. So then I look at the chart and then look at the um let me see. The H2O is a weak base, weak nucleophile.
Mm-hmm.
So then mm, so then that would be SN1 or E1.
Mm-hmm. Right here.
Yeah.
SN1E1. So that's gonna give us SN1E1 reaction. But you know how the very first step of SN1E1 reaction is to kick out the leaving group first?
Mm-hmm.
And
That's a good leaving group. So
mm-hmm. But what gets formed here? Like if we just did that by itself, like what kind of carbocation gets formed here?
um a primary
Mm-hmm.
carbocation.
Yep. And what did we say about primary carbocations earlier?
They're
Mm-hmm.
not strong enough to
Yeah.
be by
To to be by itself, right? They're
yeah.
not stable enough. So that cannot exist, right? So this is what we're gonna do, something called a concerted carbocation rearrangement, which is the tricky topic here, right? Let me write that down. Concerted carbocation rearrangement. Okay. So instead of kicking out the leaving group first and forming a carbocation here, let's just imagine that we already did that and the carbocation's right here, right? Whenever we form a carbocation intermediate, we said earlier that we have to stop and look out for carbocation rearrangement. So if we
Mhm.
look nearby it, is that a position where it can become more stable?
One, two, three. I mean, one, two. Yeah. Wait. One, two, three. Yes, it
Mm-hmm.
would be tertiary. So yeah.
Yep. Mm-hmm. And then to move that there, what can we do to rearrange that carbocation there? what is hiding from you here?
The hydrogen.
Yep. So let me draw the hydrogen out. So, how would you draw the arrow from the like the hydrogen like to move to this carbon here and kick out the leaving group?
Wouldn't you draw an arrow? Would you draw an
Uh-huh.
arrow from the H to the carbon or
Not from the H, but
from
from
the
the
carbon?
bond.
From the
This bond
bond?
right here. Yeah. This bond here is gonna move this entire H with it.
Okay.
Yep. So we're gonna draw the arrow from the bond to that carbon. What does that represent? This arrow?
The arrow represents the electrons moving
Mm-hmm. Yeah.
toward.
The electrons of this bond here are gonna move towards that carbon right there with the hydrogen. It's gonna bring the hydrogen with the bond, right?
Mm,
How many hydrogens does this carbon have right now?
um, that has which I'm sorry, that one? How much
Mm-hmm.
hydrogens?
Yeah.
Well, I mean, it has four in total, but we see two.
Mm-hmm. So how many is hiding from you right now?
Two.
Yeah, two hydrogens like this. And so if we try to make a new bond here, with let's say another hydrogen, which is this yellow highlighted hydrogen right here, this carbon, if we don't do anything else, will have five bonds. Is that good?
No.
Two, three, four, five. That breaks the octet rule,
Yeah.
right? To conserve the octet rule, what can we do? What group can we kick out?
We can kick out the bromine.
Uh-huh. The good leaving group bromine, like that. Right. So you know how before when we did SN1A1 reactions, the very first step was that we kick out the good leaving group by itself with nothing else.
Mm-hmm.
This concerted carbocation rearrangement says that we're gonna do the hydride shift and kick out the leaving group at the same time. Right. So let me
Mm-hmm.
write that down. Um, hydride shift or like carbocation rearrangement step, which in this case is a hydride shift.
Mm-hmm.
Carbocation rearrangement step
Mm-hmm.
or hydride shift
Mm-hmm.
and the good leaving group leaving happens at the same time, like that.
Mm-hmm.
Okay. Now when that happens, our intermediate is gonna look like this, right? Because we see that this carbon here, which is this carbon here, lost a bond. You know how before it had four bonds? One, two, three, four. And that's why it was neutral and happy.
Mm-hmm.
This carbon here, how many bonds does it have right now since it lost this bond?
It has three
Three bonds. Carbons with three bonds and nothing else. No pairs of electrons, no other bond. Is a positive charge. And what do we call this carbon with a positive charge?
carbon cation.
Uh-huh. What kind of carbocation is it?
Tertiary,
Yep. Tertiary carbocation. That's good.
which means it's great.
Yep. It's great. It's stable to exist by itself.
Mm-hmm.
B or minus is it gonna float around somewhere by itself
Mm-hmm.
nearby?
Mm-hmm.
Okay. Now from there, we could do the SN1 reaction. What's gonna attack this positive charge here? What do we bring in?
The
Uh-huh.
H2O.
The H2O in this case, because we have it on the arrow. So
Mm-hmm.
H2O comes in.
And then you want to go ahead and then take two of those and
Mm-hmm.
add it extra bond
Mm-hmm.
to show the O and the H with the two bonds.
Mm-hmm. Does this part make sense for here on how I got to here?
A little bit. I see what you mean. I get it. There's two H's and then there's the O with the two extra ones since you already used the other
Mm-hmm.
two.
Mm-hmm. Where did this other two come from? Like what did that other two become? Like the one that I used as an
It
arrow.
became the bond.
This bond right here.
Yeah.
Right? That this pair of electrons here is that bond
Mm-hmm.
right there.
Mm-hmm.
This circled H2O right here is this circled H2O right there.
Mm-hmm.
Right? And then let's say I scribble this like three group thing, right?
Mm-hmm.
That scribble three group thing is like right here, right?
Mm-hmm.
This is the new connection between them, which came from this pair of electrons right there. Yeah, you
Yeah.
got it. You got it. Right. And this oxygen here is positive charge because when we do six minus how many it has, one, two, three, four, five, six minus five is positive one. Like that.
Mm-hmm.
Now what can we
Yes.
do to neutralize it and make it stable?
What we can do to neutralize it and make it stable now.
Mm-hmm.
Mm, would you take another?
Mm-hmm. Another
I.
H2O as a base.
Mm-hmm.
Right. Okay. Another H2O as a base. Okay. And then that right there is what is that going to do to get rid of? to deprotonate this and make it neutral.
I don't know.
Yeah. So if we want to make this neutral right here, we're gonna have to grab a proton, right?
Mm-hmm.
And then the two electrons right here of that
Mm-hmm.
bond, they're gonna have to break and go onto the oxygen like that.
Oh.
And that's our final answer right there.
Okay.
Hmm.
I see. Where did you get? Oh, okay, and then the H3 is
Yeah,
extra.
this came from the water because you know how this
Oh
oxygen
yeah.
here gained another H right there? Like
Yeah.
H2 became H3 because it grabbed that H right there. And because oxygen has three bonds and pair of electrons, positive charge, like that. This is a side product, byproduct though.
Okay.
Okay.
Got it. Mm-hmm.
Okay. Okay. So the practice problem that you gave me, number three, was draw the mechanism for this right here,
Mm-hmm.
which is very similar to what we just did,
Mm-hmm.
right? Like that. Okay. Now, using this right here, which is very similar to this, describe to me the mechanism.
Okay. See. Sorry. Okay, that's gonna be. Wouldn't it be wouldn't it be tertiary?
So this right here is tertiary, but this isn't directly attached to the leaving group, right? This is the good leaving group. This right here is the carbon directly attached to the good leaving group. So we're not worried about this one. We're worried about this one here.
Oh, sorry. I thought we were doing the one from my homework because that one looks different.
Oh, the one from your homework is gonna be right here, right? Unfortunately, the previous reaction suffers. Oh, okay, okay, yeah. So the previous reaction they're talking about is this right here,
Mm-hmm.
right? So you know how this is an alcohol?
Mm-hmm.
Let me talk about this. This alcohol here is a bad leaving group, right? If we react it with strong acid, HBr, like alcohol is very basic. So this alcohol here is gonna get protonated. So this
Mm-hmm.
oxygen here is gonna grab the hydrogen from the HBr, kick out the Br, and it's gonna make a good leaving group. And this oxygen here is positively charged because this oxygen has three bonds, one, two, three, and a pair of electrons, right? And think of that as just like a Br.
Mm-hmm.
We call this oxonium ion. And then from there, we could do the regular SN1 reaction we've been doing. So from that point right there, your practice problem, it would be like this. Like if you had alcohol and you react it with HBr, the first step is to make the good leaving group. And then once you have the good leaving group, your nucleophile is going to be the Br minus. This substrate here is a primary unhindered substrate because you know how it's attached to one other carbon, but the
Mm-hmm.
carbon it's attached to is branched, right? And so because it's primary unhindered, we cannot do SN1 by itself like that, because what would that form? That would form a primary carbocation. And what did we say about
Yeah,
primary carbocations? We don't want that.
we don't.
Right. But look nearby. Is that stable for carbocation to exist at that this position right here?
Mm-hmm.
Yep. So because that is, we're gonna do a concerted hydrate shift. There is an invisible hydrogen there because this carbon here has three bonds. So we're gonna shift this bond with the hydrogen over, kick out the good leaving group, and that's gonna give us this positive charge right here on that carbon right there. Because like this carbon lost the bond right here.
Mm-hmm.
Right.
Mm-hmm.
Now from that, you know how we have a Br minus floating around, which is this Br
Mm-hmm.
minus right here. That Br minus floating around will attack the positive charge and give us our final product,
Okay.
which is that right there, like that.
Okay.
Okay. I'll send you the notes of this and the recording of this for you to review as well, so that you could like explain it to yourself again or practice
Mm-hmm.
similar problems. But good luck on your test tomorrow, Emily. And I will have office hours like Saturday, Sundays, 9 to 11. And if you want like private sessions or like a package deal,
Uh,
just let me know and then I'll let you know.
okay,
Yeah.
perfect. Thank you so
Mm-hmm. Of
much.
course, Emily.
Thank
Good
you.
luck.
Good luck. Thank you.
Mm-hmm.
Bye-bye.
Bye bye.